Hello children, in today's class we are going to discuss the entire chapter of radioactivity. Children, this class is very useful to to revise the chapter in a less time. So if you want in detail what we can say explanation of the radioactivity chapter, just go to the description where links will be given where each and every topic is covered in detail and each and every topic is discussed in detail. So today's class children, only we are going to have a quick revision. At the same time, we are not going to miss any point in this video children. Each and every topic is discussed, but in a shortcut I'll tell you how to revise. This class especially is a very useful just before going to write exam. If you want to revise the entire chapter, yes, be with this video so that you have a good revision of radioactivity chapter. Children, mainly in this chapter we have two units. In a unit A, they covered about actual types of nuclei, radioactivity and alpha, beta, gamma radiations. Their properties, decay, radioisotopes, precautions while handling the nuclear energy, background radiations. Finally, in a unit B, they covered about nuclear fission and a nuclear fusion. Now children, first let us see once again atom structure, means how the atom is, structure of an atom. First let us try to see about the atom children. Children, we know that here atom is consisting of course many particles will be there. In that there are three fundamental particles. What are those? Electrons, protons and neutrons. So let us see once again here, means so here these protons and neutrons, they will stay in the nucleus, whereas here electrons will be revolving around the nucleus in a particular shells or orbits. Children, here very important thing is that as long as electrons are revolving in the particular shells or orbit, they neither lose energy nor gain energy. That's what these shells or these orbits only we can call it as a stationary shells. Stationary shells or orbits. Shells or orbits. Stationary shells or orbits. Is that clear? Fine children. So here depends on the number of electrons. This number of shells mainly depends on the number of electrons. Am I clear? Fine. So each and every shell is a given special name. K shell, L shell, M shell like this, N shell, O shell like that. Then here the very important thing is that here how many maximum number of electrons can accommodate in a given shell or a given orbit. So it depends on a principal quantum number children here. It's very important. First of all, how to calculate the number of electrons which can accommodate, maximum number of electrons which can accommodate in each and every shell. So that can be calculated with the help of children 2n square. So this formula is very important. Here what is n children here? N is a number of shell. For a K shell, n is equal to 1. For L shell, n is equal to 2. For a M shell, n is equal to 3. So if you want to calculate the maximum number of electrons which can accommodate in a particular shell, yes, substitute n value. With the help of this formula, you get that maximum number of electrons which can accommodate in a particular shell or orbit. Is it clear? Fine children. Now come to the size of the atom children. So here size of the atom depends on the number of shells children. Number of shells depends on the number of electrons. But where the size of the atom depends on number of shell. It's very important. What here? For example, if you want to find the radius of the atom children, what is the radius of the atom here? From the center to the outermost orbit. This only we can take it as a radius. If number of shells increase, obviously radius increases. As radius increases, the atomic size also increases. Is it clear? Fine children. So here atom size of the atom is measured in terms of angstroms. So on average, the size of the atom is 10 power minus 10 meters. Clear? Fine. So in an atom, what will be there here? Protons, neutrons and electrons. Children, here, what is very important? The mass of the electron is, the mass of the electron. First let us see the charge children. So here, the charge of the electron. Let us talk about the charge mainly. So charge of the electron. For electron it is minus 1.6 into 10 power minus 19 coulomb, whereas the charge of the proton, children, the charge of the electron and the proton is same, but in opposite. So this will be plus 1.6 into 10 power minus 19 coulombs. Children, neutron is electrically neutral. Then what is the charge of the whole atom, children? It's very important. Atoms are electrically neutral because here, as the number of electrons are equal to the number of protons, plus charge is equal to minus charge. On whole, what is the charge of the atom? 0. Fine. Okay. Now comes to the mass, children. So here, mass of the electron, children, it is 9.1 into 10 power minus 31 kg, whereas mass of the proton is 1.672 into 10 power minus 27 kg, whereas mass of the neutron is equal to 1.674 into 10 power minus 27 kg. If you can see, there is a slight difference in the mass of the neutron and mass of the proton. Maximum cases, we can take mass of the neutron as equal to the mass of the proton. Now, when we compare the mass of the electron with the mass of the proton, children, it is found that mass of the electron is 1 by 1840 times than mass of the proton. I mean, the mass of the electron is 1840 times less than that of the mass of the proton. Clear? So, this is about the atom. Is it clear, children? Fine. Now, we will see about the particularly about the nucleus. Can you erase this? Okay, now? Come on. Yes, fine. So, one second. Yeah, fine. Now, let us talk about the nucleus. Let us talk about the nucleus. Fine, children. So, this is a, I can say in a, if you want in a simple terms, simply it is a middle part of the atom. We can say that. Actually, we should not say that. Generally, I am telling you. So, here this nucleus will be there at the center of the atom. Then what will be there in the nucleus, children? Yes, look at here. If you can see here nucleus, children, in this nucleus, protons and neutrons will stay. Protons and neutrons. Now let us see the charge of the nucleus. Children, inside neutrons will be there whose charge is 0 and protons are there whose charge is positive. So this is plus, it is 0, which means what? On whole, what will be there? Plus only it will be there. So the charge on the nucleus is positive. And one more important thing is that the charge of the nucleus is only because of the charge of the protons. Am I clear? So here, if anyone will ask you what is the charge of the nucleus, yes, you can say that is a positive charge. Positive charge, fine. And here one more important word we need to see. What is that here? Atomic number. Atomic number will represent the Z. What is the atomic number, children? The number of protons in an, what we can say, nucleus. The number of protons in the nucleus, okay, of an atom, only we can call it as a number of protons. Only we can call it as a atomic number. Clear? Fine, children. And the protons and the neutrons together we can call the nucleons. Protons plus neutrons together we can call it as a nucleons. Clear? This number of nucleons only we can call it as a mass number. So very important. So here mass number we represent with the letter A. What is the mass number, children? Yes, the number of protons plus neutrons. So let us write like this. A is equal to number of proton is nothing but what, children? Atomic number. So that is Z plus number of neutron. So mass number is equal to atomic number, that is proton number plus neutron number. If you want to find about the number of neutrons here, just you use this formula A minus Z. This formula which we use to calculate the number of neutrons. Fine. Okay. Now, children, let us see the representation of an atom. So how can we represent the atom? Let us say X is an atom, children. Some atom, let us say that, and its atomic number will write as a subscript with a Z, and the mass number is superscript. Okay, na? So based on this, we can expect one more question. So they may ask, one atom will be given, okay, and they will ask us to find the number of neutrons or number of protons and what is a mass number, like that. So example, let us see. Just one or two examples we'll see so that you'll understand. So here carbon 6, 14 children. So here if you can see atomic number is 6, mass number is 14. Okay, fine. Then what about neutron number children? Yes, neutron number A minus Z. So that is 14 minus 6. It is going to be 8. Okay, fine. Let us take one more example. Sodium 11, 23. And here atomic number is 11, mass number is 23, neutron number is 23 minus 11. It is going to be 12. Clear? So this is how we can represent an atom, and this is how actually we should calculate the number of neutrons. Fine. Okay. So now we discuss about the types of nuclei, children. Types of what? Nuclei. Children, nucleus is a singular. Nucleus is a singular, whereas nuclei is a plural. So here let us see types of nuclei. Types of nuclei. Types of nuclei. So in this, first one is isotopes. That's isotopes. So what are isotopes? So look at here, children. Let us take the example so that what will happen, it's very easy to us to understand. So here example, just let us take two examples. H11 comma H12 comma H13. Let us take one more example. C612, C614. So if you can see these two examples, children, one common thing is there, one common factor is there. What is the common factor here? Yes, these atoms having same atomic number. These three, you can see these three, same atomic number, different mass number. Here also, same atomic number, different mass number, which means what? The atoms with the same atomic number, different mass number are called isotopes. Clear? Fine, children. So here, there are two types of isotopes. First one is stable isotopes. First one is stable isotopes, children. So let me give you example, then you will understand. So let us take C612. Children, in this, number of protons are how many? Number of protons is nothing but the atomic number. So that is 6. Okay. So mass number is, let us take 12. Neutron number is 12 minus 6. This is 6. So notice number of protons and number of neutrons, both are equal. So stable isotopes means what? The isotopes in which number of neutrons are equal to the number of protons are called stable isotopes. Okay, fine. Now unstable isotopes. Unstable isotopes. So let us take the carbon isotope only, that is C614. In this case, number of protons, that is the atomic number, is a 6. Okay. Mass number is 14. What about number of neutrons here? 14 minus 6, that is 8. So if you can notice, children, here number of neutrons are greater than number of protons. And one more thing, such isotopes, okay, they are found in radioactive nature. And this kind of isotopes we can call it as even radioisotopes also. Examination part of it is very, very important. So there are two types of isotopes, stable isotopes and unstable isotopes. Okay, fine. Now children, here next one is isobars. Isobars. Look at here. Sodium 11, 23 and magnesium 12, 23. So here atoms which are having different atomic number but same mass number. Children, again I repeat, the atoms with a different atomic number but same mass number are called isobars. Actually here one more specialty is there, children. Look at here. So in this, so number of protons are 11. Okay. Number of neutrons, children, 23 minus 11, that is 12. Okay. Here in this case, let us see, number of protons are what, children? 12. Number of neutrons how many? 23 minus 12, 11. So just notice here, number of protons and number of neutrons got interchanged. So such a isobars only we can call it as a mirror isobars. We can call it as a mirror isobars. Very, very important. It's a mirror isobars. Okay, na? So fine. So what are isobars, children? Atoms with a different atomic number, same mass number, are called isobars. Okay, fine. So here last one is isotones, children. Isotones. So look at here. Third one. Third one is isotones. Third one is isotones. Look at here. Silicon 1431, phosphorus 1532. Here their neither atomic number nor mass number is same. But look at here, children. Okay. Then let us try to find their neutron number. Neutron number is equal, children, 31 minus 14. 31 minus 14. It is 17. But here also let us try to find out number of neutrons is equal to 32 minus 15. This is also 17. Which means what here? Number of neutrons are same. So the atoms in which number of neutrons are same are called isotones. Clear? Once again, children. What are isotopes? The atoms with the same atomic number, different mass number. What are isobars? The atoms with the different atomic number, same mass number. What are isotones? Different atomic number, different mass number, but same number of neutrons. If the atoms in which the number of neutrons are same are called isotones. Got it? Fine, children. Now, before going to discuss about actually radioactivity concept, children, we need to see the difference between chemical change and nuclear change. This is very important, children. So here let us say chemical change. During a chemical change, what will happen? Or during what we can say, a nuclear change, what happens? This is examination point of view. It's very important. Even to understand the concept of radioactivity, also very important. Children, during the chemical change, the orbital electrons will change. Orbital electrons. There is a change in the change. Very, very important. There is a change in orbital electrons. Orbital electrons. What about nuclear change? During a nuclear change, in children, there is a change in number of nucleons. Number of nucleons. Very, 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 very important. Very means what here? On this chemical change, children, what again? So there is an impact of pressure, there is impact of temperature, there is impact of oxidation, reduction, heating effects. All these things will change the number of what we can say orbital electrons. So that there will be what we can say chemical change will depend on all these physical conditions and chemical conditions also. But whereas nuclear change does not depend whether you can heat it, whether you can raise the temperature, you can change the pressure, whether it will go undergo oxidation, reduction, there is nothing change. Okay, fine. And here this chemical change can occur at a room temperature also. I mean what here? The energy required is very less. Energy required is in terms of electron volt. But whereas the energy required here for a nuclear change is in terms of mega electron volt. So if you can compare the energy required for a nuclear change with the energy required for chemical change. So energy required for nuclear change is almost 10 power 6 times than that of the energy required for a chemical change. Is it clear? So only one point here important. Here orbital electrons will get impacted. Orbital electron will be changed. Here number of nucleons will be changed. That is what? Either protons or neutrons. There is a change in the orbital electrons. So whenever there is a change in the orbital electrons, yes, that is a chemical change. Whenever there is change in the nucleons, number of nucleons, then that is what actually? That is nuclear change. Done? Fine. Now come to the radioactivity. Children, actually this radioactivity is a unplanned, means accidental discovery. Okay, so whatever it may be, it was discovered. So but it is not a planned, children. So it is not a pre-planned. Okay, now fine. So the scientist called Henry Becquerel, so accidentally discovered this radioactivity. So he found that one day, so he found unexpectedly, with unplanned, again I'm telling you. So he found that some, it's like a uranium salts, kind of a uranium salts, they're emitting some radiations, and they are showing the impact on this photographic plates. Means photographic plates are affected by the a kind of radiations which are coming from the uranium salts. First he didn't know what to call. So then what happened? First he named those radiations as a Becquerel rays. With his name only, yes, just he called. So what he called first, these radiations? So he called these radiations as Becquerel rays. But later children, so many experiments, after so many years, so after series of experiments, yes, scientists, they could find that, yes, so these materials like a uranium, they are emitting kind of radiations, and these radiations are consisting of alpha, beta, gamma. Okay, fine. And here we need to understand one important point, important word. What is that here? Radioactive material. Radioactive material. Radioactive material. Example, uranium, thorium, plutonium, neptunium. All these things are radioactive materials only. Children, usually the atoms with greater than atomic number greater than 82. Okay now. So they are unstable in nature. Usually the number of neutrons are greater than the number of protons. So they are unstable. To get stability, children, they go on emitting radiations. Such a material only we can call it as a radioactive material. So as I told you that these radiations are consisting of alpha, beta, gamma. Now we will see the properties of alpha, properties of beta, properties of gamma. Then we will see their decays also. So first we see properties of alpha, properties of alpha particles, properties of alpha particle. Children, examination point of view, they might ask for 1 mark. I mean, they don't ask you to write all properties. So based on properties also questions can be asked. Okay, fine. So first point, children, these alpha particles are, alpha particle is consisting of 2 protons, 2 neutrons. I mean 2 protons, 2 neutrons. You can imagine if they are bound together. 2 protons, 2 neutrons, they are bound together. It is nothing but actually it's a alpha particle. Okay na? So here means simply, okay, 2 protons and 2 neutrons. So it is nothing but children here helium nucleus. Very, very important. It's nothing but helium nucleus. Helium nucleus. Or you also can say that doubly ionized helium means if helium is ionized twice, if see helium is consisting of 2 electrons. If 2 electrons you can remove, what will be left? Only nucleus in which 2 protons and 2 neutrons will be there. So in exam they may ask a question. For example, for this alpha particle, if alpha particle will absorb 2 electrons, it will convert into helium. Very important. So let me tell you. So for example, it is 2 protons, 2 neutrons. This I can call it as an alpha particle. Somehow, if it can just accept 2 electrons, then what will happen here? 2 protons, 2 neutrons, and 2 electrons will be revolving. This is nothing but helium. So if alpha particle will capture 2 electrons, children, it will convert into helium atom. Okay, fine. Now what is the charge of this alpha particle? Children, you can hear in this neutrons are there, protons are there. Neutrons are 0 charge, protons are positively charged. So on whole the charge of the alpha particle is positive. So here alpha particles are positively charged particle. Alpha particles are positively charged particles. And what is the charge, children, here? The charge of the alpha particle is double the charge of the what we can say proton, twice it is. For electron means minus, proton means plus E. So here 2 protons are there plus 2E. And what about mass, children, here? Mass of the alpha particle is 4 times of the mass of the proton. Children, as I told you that here there is no much difference between the mass of the proton and the mass of the neutron. Both will take as the same. So here total I can say 4 number because mass is same, right? So that's what I am saying. Mass of the alpha particle is 4 times the mass of the proton. And children, here the speed of the alpha particle is the speed of the alpha particle is around 10 power 7 meter per second. And come to the ionization energy. It's very, very, very important. Means as alpha particles are having what we can highest charge compared with the beta and gamma, and they are the heavy particles. So whenever they are passing through a particular medium, they have an ability to ionize the atoms. So compared with the beta and gamma, the ionization power is a very high. So in exam they'll ask us to write the order. So alpha means ionization power of alpha particles is very much greater than the beta than gamma. So it is ionizing power. Ionizing power comes to here. Alpha is greater than, beta is greater than gamma. It's almost 100 times, children. So if you want, alpha is equal to 100 times than beta, and beta is equal to 100 times than gamma. I mean what? If you want to compare alpha and gamma, alpha is equal to 10,000 times than gamma. So this is what actually, this is about what we can say, ionization power. Are you able to see the board? Let me check. Yes, fine. Very well it is seen. Clear. Fine. So now children here, so this is about the ionizing power. Now come to the penetrating powers, children. So as the speed of the alpha particle is less than beta and gamma, and the penetrating powers also very less. So here penetrating powers are very less, that is alpha is less than, beta is less than gamma. So here alpha is equal to 1 by 100 of beta, and beta is 1 by 100th of gamma. Is that clear? Fine, children. And here next one is very important, biological damage. So alpha particles will do the less biological damage. Children, less means don't think that they are very friendly particles. They are dangerous. But compared with the beta and gamma, penetrating powers are very less. Is that clear? So because their penetrating powers are very less, so they will do less biological damage when compared with the beta and gamma. They are danger, but compared with the beta and gamma, they will do less biological damage. Okay, na? Fine. And as usual, these alpha particles will show the effect on photographic plates. Clear? So this is about a alpha particle. Now children, here only we see the alpha decay. Alpha decay, here only we will see, children, just back to back. It's very important. First children, even it's my suggestion that first you learn alpha properties, then immediately learn about alpha decay also, because you know the concept of alpha particle, right? Okay, so alpha particle means what, children? Here alpha particle is 2 protons, 2 neutrons. This is Z, together it is A. So Z is equal to 2, A is equal to 4. So we can represent alpha particle with a Z, helium 2, 4. Don't get confused, children. The symbol is same like a helium only. See, again I'm telling you, alpha particle carries 2 protons, 2 neutrons, which means what? It carries 2 units of atomic number, 4 units of mass number. So whenever alpha particle is emitted from a particular nucleus, the atomic number of that particular nucleus is reduced by 2, mass number is reduced by 4. Okay, now fine. So now let us see that it's a alpha decay. Children, as I told you that this radioactive material, they go on emitting the radiations. If that radiation is consisting of alpha particle, then it is called alpha decay. Now let us see. First suppose, children, here X is a nucleus, its atomic number is Z, mass number is A. Children, if it emits one alpha particle, then what will happen here? Alpha particle carries, as I told you, 2 units of atomic number, 4 units of mass number. Then what will happen? The atomic number of this parent nuclei, this is called parent nuclei. It's called parent nuclei. Atomic number of parent nuclei is reduced by 2. So there is a change in atomic number. Children, whenever there is a change in atomic number, there is a change in the nucleus. So here we are going to get a new nuclei. It's called Y. It is called daughter nuclei. It is called daughter nuclei. And even mass number also is what? Even alpha particle is carrying the 4 units of mass number. So the parent, mass number of the parent is reduced by 4. So it will become A minus 4. Let us see the example here. Yes. So the best example is uranium 92, 238. Okay, 238. Now it emits one alpha particle, He24. So atomic number is reduced by 2. So it is a 90. And the atom with the atomic number 90 is a thorium. Okay. And 238 minus 4, it is 234. That's it. Children, in all types of nuclear reactions, atomic number and mass number is conserved. which means what here, reactant atomic number must be equal to the what is the atomic number together, means the total atomic number of the products. The mass number of the reactants must be equal to the mass number of the what we can say products. For example, look at here. Here left side is a 92. 90 plus 2, 92. Okay. 238 here. 234 plus 4. It is a 238. Clear? Fine. So this is about the alpha particles properties, and here alpha decay. Alpha decay. Clear? Fine. Now children, let us see about the properties of beta. Properties of beta. So properties of beta particles. So beta particles properties, and immediately we also can see the beta decay. Children, here beta particles are nothing but electrons, but not electrons, children. Not electrons. So I can say these are negatively charged particles. Negatively charged particles. See, the charge of the beta particle is equal to charge of the electron. The mass of the beta particle is equal to mass of the electron. But the difference is that the kinetic energy of the beta particle is very much higher than that of the kinetic energy of the alpha particles. And one more difference is there. Electrons are what emitted from the orbital, or what we call the orbits, shells. But whereas your beta particles, they are emitted from the nucleus. How? Let us see, children, here. So here, one unstable neutron will decay into one proton and one beta particle, which means what here, one neutron gets what we can say decayed into proton and beta particle. So which means what, during beta particle, children, one neutron is converting, which means what, the number of neutrons are reduced and the number of protons are increased. So this point is very important. This point is very important. Once again, we will take this point when we are discussing the beta decay. First, let us see the properties. So these are the negatively charged particles. First point, let us say negatively charged particles. Fine, children. Now, as I told you that the charge is equal to the charge. The charge is equal to the electron charge, and even mass also equal to the mass of the electron only. Mass of the electron. Now, come to the speed, children. The speed of the beta particle is in the order of 10 power 8 meter per second. That is greater than that of the speed of the alpha particles. Okay. And children, these beta particles are very light than that of the alpha particle. That's very important. The mass of the beta particle is almost negligible, like electrons. Okay. But alpha particles are very heavy particles. Their mass is very heavy. The mass of the alpha particle is 4 times than that of the mass of the protons. Okay. Fine. So this is mass. Now children, when come to the ionizing powers, ionizing powers. So ionizing powers are of the these beta particles in between alpha and beta. I mean, so it is ionizing power is less than alpha, whereas greater than gamma, in between. Okay. Even children, penetrating powers also, penetrating powers also in between alpha and beta. But come to the penetrating power, beta particles is greater than alpha but less than gamma. And these beta particles also causes biological damage. Compared with alpha, more biological damage. Compared with gamma, less biological damage because of penetrating powers. Okay, fine. And here one more thing is that yes, as like alpha particles, beta particles also show the effect on photographic plates. Clear? Fine. So now we see it's about the properties of beta particle. Now we see the beta decay. So if the radiation is consisting of beta particle, then we can see the beta decay. So let us see what will happen during beta decay. Children, let us recall what will happen during alpha decay. During alpha decay, atomic number is reduced by 4, mass number is reduced by 4. Atomic number is reduced by 2 and the mass number is reduced by 4. Okay, fine. So now it's a beta decay. So let us take one atom, some P, whose atomic number is Z, mass number is A. Now here one beta particle is emitted, -1, 0. So beta particle is carrying one negative charge, -E, let us see that. So here the atomic number of parent daughter nuclei will become Z plus 1. Here Z Z plus 1 minus 1. Yes, atomic number is conserved. Here we will get a new nuclei. This is called daughter nuclei, parent nuclei, and there is no change in mass number. So example, let us see. So carbon C614 emitted one beta particle. So here 6 minus 1, atomic number should be increased by 1, so it is a 7. So the atom with atomic number 7 is nitrogen, nitrogen 14. So here during a beta decay, atomic number is increased by 1 and there is no change in mass number. So why there is no change in mass number? Look at here, children. For suppose here it is an atom. In this there are 3 protons, 3 neutrons, let us say, just example I am telling you. And here what is happening during beta decay? One neutron is converting into one proton on a beta particle. So which means what here? Neutron number it is going to convert, which means what? One neutron is decreased. So 2 neutrons. And whatever the proton is released, it is added to the nucleus. So 3 protons plus 1, 4 protons. And one beta particle is emitted. One beta particle is emitted. Okay, that's fine. Now for this, just look at here, children. What is the atomic number? 3. Okay. Mass number is what? Number of nucleons. 3 plus 3, 4 only. Now come to here. Atomic number, number of protons, 4. Mass number, number of neutrons plus number of protons, 2 plus 4, 6. Oh, this is 6, sorry. It is a 6. So if you can see, atomic number is increased by 1 and there is no change in the mass number. So this is all about the properties of beta and beta decay. And one important thing, children, just try to notice these 2 nucleus here. Both are having different atomic number but same mass number. Means whatever the daughter nuclei which is produced is a isobar to the parent nuclei. It's a very so in exam they'll ask a question, what is the special name given to the daughter nuclei in the beta decay? It is what actually? Isobar. Fine. Now let us see about the gamma radiation. Children, generally we can say alpha particle, beta particle, but here we can say gamma radiation. Why are you saying it is a gamma radiation? Yes, so these do not possess mass. These do not possess mass. So particle means should possess some mass. Gamma radiation. Children, gamma radiations are electromagnetic. They are part of electromagnetic waves. Okay, fine. And the speed of the gamma particle is equal to the speed of the light in a vacuum. That is 3 into 10 power 8 meter per second. And what about charge, children? Here there is no charge. Charge is 0. What about the mass? Mass is 0. Okay, fine. Come to the ionizing power. Ionizing power. So come to the ionizing power. Very less ionizing powers compared to the beta and gamma. That is gamma is less than, beta is less than alpha. Okay, fine. And come to the children here. Penetrating powers. Penetrating powers, children. Yes, penetrating powers are very high. Gamma is greater than, beta is greater than alpha. Very much high. That's what these will do severe biological damage compared with the beta and gamma. Very severe biological damage. So because of this reason only gamma radiations are used to cure the cancer. Okay, and as like alpha and beta, gamma also can affect the photographic plate. Now come to the gamma decay. Children, let us recall about alpha decay and beta decay. During alpha decay, atomic number is decreased by 2, mass number is decreased by 4. Whereas during beta decay, atomic number is increased by 1 and there is no change in mass number. But come to the gamma decay, children. Look at here. So, and one more thing, this gamma will come into play immediately after alpha or beta. See, a nucleus emitted alpha particle and immediately don't expect alpha will come, beta will come. No, gamma will come. And after emission of beta particle, again second alpha beta won't come. Immediately what will come? Gamma will come. Because either emission of alpha or beta, children, the nucleus is in excited state. In excited state, children, it has excess energy and the lifetime is very less. So what will happen? It comes to ground state by releasing the energy in the form of gamma decay. So if you can see, X is an atom, for example, Z is atomic number, A is a mass number. So this star represents excess energy. So this X energy is released in the form of gamma, and as usual it is Z and A only, which means what? There is no change in atomic number, there is no change in mass number, but children, there will be a change in the nucleus energy. There will change the nucleus energy. Let us see the example, children. So after, in alpha decay, after what from uranium, one alpha particle is emitted, what we got? Actually thorium we got. Yes, thorium, it is 90 to 34. Yes, it has excess energy. This excess energy released in the form of gamma, and here thorium is left 90 to 34. So during a gamma decay, there is no change in atomic number, there is no change in mass number, only there is a change in the nuclear energy. There is a change in the nuclear energy. So children, this is all about properties of alpha, beta, gamma, and alpha decay, beta decay, gamma decay. Children, based on this only, we will be having questions even in board exams also. Now children, let us see about the radioisotopes. Radioisotopes. Children, it's a very important examination point of view. Radioisotopes. Generally, children, we know that the atoms with the atomic number greater than 82 are unstable. But children, it is also noticed that isotopes of some elements whose atomic number is less than 82, in which number of neutrons are greater than number of protons, they are found to be in radioactive in nature. Radioactive in nature. Such a isotopes only we can call it as a radioisotopes. Example, children, here carbon 14, potassium 40, cobalt 60. Children, there are so many applications of radioisotopes. We have applications in a medical field, industry field, okay, so means scientific. Many applications we have. So let us see, children. So few applications, let us see. First one, children, these radioisotopes, especially here gamma rays which are emitted from the cobalt 60 gamma radiation, so which are used to cure, children, or we can say cancer, so called radiotherapy. They are used in a radiotherapy, used to cure. Okay, now here carbon 14 is used in a what we can say carbon dating, with which we can what archaeology department people, they'll try to find out the age of the rocks. Okay, carbon dating. And here, children, here radioactive sodium chloride, radioactive iron, radioactive iodine, these three are called, children, tracers. These three are called tracers. So which are used to find if there are any clots, blood clots or tumors in the brain. So these tracers are used to detect the what we can say tumors in the brain or clots in the blood. Okay, fine. And the next one, children, so in industries, what will happen as a machine parts are continuously in motion, so that there is a chance of accumulating some charges on the surface of the metal bodies. That is too dangerous. So then how can we remove those charges? Yes, by using what we can say radioisotopes only. Means by using radiation which are emitting from the radioisotopes are used to remove the what we can say the accumulated charge. So here accumulated charge can be removed. Accumulated charge can be removed. Even, children, if you want to control the thickness of the paper, and even, children, we also can use the alpha particles which are emitted from the radioactive isotopes. They are used in what we can say nucleus transportation. Is it clear? So these are the applications of the radioisotopes. So radioisotopes definition and applications are very important examination point of view. Clear? Fine, children. Now, what are the precautions to be taken while handling the what we can say nuclear energy? Achha, before that, children, we will see the sources of harmful radiation. Sources of harmful radiation. harmful radiation. Children, here we know that sometimes we all know that yes, with the nuclear power plants will be there, with which we can produce the electricity. If everything goes fine, it's well and good. But sometimes due to the technical issues, what will happen? So there will be some blast. So during that, what will happen, children? Yes, or see, there completely they'll be used radioactive materials, right? So then what will happen, children? That radiations will be coming out. So it is nothing but it is going to act like a source only. So here the first one is what? Radioactive fallout. Radioactive fallout from nuclear reactors. Fine. And the second one is nuclear waste. Nuclear waste. Children, in a nuclear power plants, fuel rods are made up of generally uranium. Okay. So they'll be using. But after some days or after some months, what will happen, the amount of radiation which is emitted by that fuel rods will be reduced automatically, Then what will do? Those fuel rods are rejected. So these fuel rods which are rejected because there what we can say the ability to emit radiation is decreasing are called, we can call it as a nuclear waste. So nuclear waste is nothing but the fuel rods only, but their strength gets decreased so that they are rejected. So they are also called nuclear waste. They are called actually nuclear waste. And third one is children here cosmic rays. Yes. So here cosmic rays also consisting of many harmful radiations. Okay now? Fine. Now children, let us see harmful effects of these harmful radiation. Okay, or effects of harmful radiation, we can say. So effects of harmful radiation or harmful effects only. So here we have two types of radiation, effects. So first one, children, let us the short term. So this short term are curable, means if a person will get any health issue due to this radiation, yes, so he can be treated. So he may be recovered in a few days, few months or a few years. Okay, fine. And the second one is long term. Actually, in fact, these two comes under one category. Long term. In this long term leads to the person death. You may get one doubt, sir, person only dying actually. Then how do you long term, right? It's a closed. Life is ended. Yes or no? Yes, children. So here in a short term means these two is about only one person. The person who will undergo this effect of this radiation may get some health diseases. Okay, so whenever he'll get some disease, he might be cured. Then it's called short term. He is not cured. He might die last. So that is called long term. Other than this, children, we have third one, permanent. It is, children. Permanent. What is this permanent here? Already person is dying, right? Again, what will be left to suffer here? Yes, children. So in this case, what will happen? There will be change in the genes. Genes is modified so that what will happen? It is carried to the next generation. In these two children, in these two cases, only one person will suffer and that person only will die. See, I am not saying that it's a good thing, children. So let us not wish that actually. So no one should suffer, children. No family should suffer actually. Everybody should be happy. All families should be happy. Let us wish for that. But in a worse situations, I'm talking in a worse situation, children. I'm talking of worse situations. A person only will suffer, a person only will die. But here it is not like that. Person will die, but still that is carried to the next generation. That is called actually permanent change. Okay, fine. Now we discuss the what we can say, what precautions, safety precautions while handling the nuclear energy. Precautions while handling the nuclear. Again, in this there are three parts. Three parts. What is that? A person who is working in a what we can say in a nuclear reactors. What are the precautions he should take? And what are the nuclear waste which we will get? How it should be disposed properly? Third one, while establishing a nuclear power plant, what are the precautions to be taken? Three there are. See, under this, what we can say, children, precautions to be taken while handling a nuclear energy. There are three stages, so three parts, let us say. First, children, let us come to the person. If the persons who are working in nuclear reactors, what are the precautions to be taken? Yes, they are provided with lead gloves, lead lined aprons. Why, children? Somewhat this lead material will stop the radiation. Okay, fine. So because the person is wearing the lead gloves doesn't mean that he can touch the radioactive material physically. No, should not touch. So for that they should use long lead tongs in order to deal with the radioactive materials. But still there is a chance that the person will get exposed to the radiation. That's what safety badges must be given, so that they will measure to what extent the person gets what we can say exposed to the radiations. So based on that, yes, some what we can say again, some what we can say, if a person is undergoing too much exposure to the radiations, definitely precautions will be taken immediately. Okay, this is about the one person. Okay, and what about nuclear waste? What about the nuclear waste, children? What we get, we should not throw outside like a normal waste. Children, I'm not saying that we should throw normal waste also. Even, yes, we should not throw even small unnecessary dust also out of our house actually. So let us follow the Swachh Bharat. Swachh Bharat is very, very important, right? Yes. So it is our family, it is our state, it is our nation. Let us make it clean. So every one of us should have this responsibility. So it's a normal dust means, yes, anyone can handle, but nuclear waste is not like that. So we cannot keep wherever we want, children. So whatever the nuclear waste which is obtained, children, first they must be kept in a lead casket, and they must be taken to very far from the people. So there shouldn't be any population, nothing should be there. There it should be buried in deep, and there must kind of a symbol should be placed that it's a red zone or something like that. Okay, now fine. And come to the nuclear power plants, children. If you want to establish a nuclear power plant, first of all, that should be very far from the populated area. The second one, there must be a backup cooling system, because nuclear reactor is nothing but what, children? It's steam engine. Continuously it is producing the heat. Continuously it is producing the heat. So that there must be a backup cooling system. The third one, yes, that core of the reactor. So it's completely surrounded by a one lead material thick wall. And finally, entire power plant must be covered with a very thick concrete wall, because this concrete wall also somehow can stop the radiations. So these are the precautions to be taken while handling the radioactive or nuclear energy. Now children, here background radiations. So here it's a background. Okay. Background radiation. So in exam they may ask you the question also even. Background radiations. What are background radiations, children? So even though means even in the absence of radioactive material, we will get exposed to some radiations. So you cannot see, you cannot find that radioactive material, but still our body will get exposed to some radiation. Such radiations are called background radiations. So there are two types of background radiations. First one is internal background radiations. First one is internal background radiations. Here example, C14 potassium 40. Second one is external background radiation. Example here, it's a cosmic rays, yes, cosmic rays, yes, and here radon 222. So these are the internal background radiation, external background radiation. Children, once again, what are background radiations? So the radiations to which we all are exposed, even in the absence of, even the virgin radioactive material is not seen, are called background radiations. And it is highly impossible to keep our body away from the background radiation. Somehow our body is exposed to the radiations. Clear? Fine, children. Now let us talk about the nuclear energy. Let us talk about the nuclear energy. So before that, let us recall once again law of conservation of mass. Whatever may be the reaction, children, mass should not get wasted as like a energy. Energy also should not get wasted. Clear? Fine. Now children, for example, let us take two equations. Okay, for suppose let us say x is a product and it got split into y and z, let us say y and z. So then what do we expect actually? mass of the x must be equal to the mass of the y plus mass of the z. Okay, nothing is wrong, fine. And the second type, let us take that here. P plus Q together, they combine to form some R, let us say that. Okay, now fine. So here, what do we expect? The mass of the P plus mass of the Q must be equal to the mass of the R. Generally, what we expect, children. But what is the reality, what is the reality? The mass of the X is always greater than the mass of this one. And here mass of this one is greater than that of the mass of the R, which means what? It is found that mass of the, in any reaction, the mass of the, especially when talking about the nuclear, children, I am talking about the nuclear reactions. I am talking, especially here we are talking about the nuclear reactions. In any nuclear reaction, children, the mass of the products is always greater than that of the mass of the, reactants is always greater than that of the mass of the products. Or we can say like this also, the mass of the products is always less than that of the mass of the reactants, which means what? Some mass is missing here. Some mass is missing. So whatever the mass which is disappearing during nuclear reactions is called mass defect. It's called a mass defect. We'll represent with the delta M. Where this mass is going? Yes, for this question, where this mass is going? For this question, the answer is given by Einstein mass energy equivalent theory. That is what, children, here E is equal to delta M into C square. Here delta M is mass defect, C is what? Speed of the light, which is 3 into 10 power 8 meter per second. So here what Einstein said that yes, whatever the mass which is disappearing is converting into energy. That energy only we are calling it as a nuclear energy. So the mass is disappearing and it is appearing as an energy. So what are the energy which is produced during the nuclear reactions is called nuclear energy. Is called what? It's a nuclear energy. It is called nuclear energy. Then how can we calculate this nuclear energy? Yes, by using this formula we can calculate nuclear energy. So if some x amount of mass is disappearing, obviously the equivalent energy must be released. For suppose, children, let us example. If 1 kg mass disappears, how much amount of energy is released? Look at it. We can calculate. So in the place of delta M, you put 1. Okay, 1 kg. Let us write here so that you will come to the units also. 1 kg into C square means 3 into 10 power 8 meter per second whole square. This is 9 into 10 power 16 kg meter square per second square. It is nothing but joule. So it is 9 into 10 power 16 joules, children. So here this much amount of energy is released if 1 kg mass disappears. Children, usually the energy is expressed even in terms of kilowatt hour also, and we have a relation between joule and kilowatt hour. What is that, children, here? So here 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. Okay, so by using this relation, so if you can do, you will get E is equal to 2.5 into 10 power 10 joules. 10 power 10 joules, this is R. So if you want the energy equivalent to the 1 kg of mass, so 9 into 10 power 16 joules, or in terms of, kilowatt hour, kilowatt hour. So from this we can write here 1 joule is equal, children, 1 by 3.6 into 10 power 6 kilowatt hour. So in the place of joule you can substitute, then you will get it as 2.5 into 10 power 10 kilowatt hour. But children, whenever we are dealing with the subatomic particles, neutron, protons, do you expect that the mass will be in terms of kgs? No. So the mass of the subatomic particles we express in terms of AMU. AMU. What is AMU, children, here? 1 AMU is nothing but the 1 by 12th of mass of C612. So which is equivalent to the 1.67 into 10 power minus 27 kg. The question is that if it's the first one, second example, this is the first one, 1 kg mass. What if 1 AMU mass disappear? 1 AMU mass disappear. How much amount of energy is released? Children, even examination point of view, it's very important. So if 1 AMU mass disappears, children, we get 931.5 mega electron volt energy released. Children, very important. If a mass of 1 AMU disappears, how much amount of energy is released, children? Here 931.5 mega electron volt. Clear? Fine. Now we discuss the types of nuclear reactions. Here we have two, children. Hope you copied this. Okay, that's fine. Now first we discuss about nuclear fission. Nuclear fission, then nuclear fusion, then after that happy ending. What will be there? Because the last topic is nuclear fusion. So first let us discuss about a nuclear. First let us discuss about a nuclear fission. Nuclear fission. So in this, what will happen, children? Here in the simple terms, I'll tell you, a heavy nucleus when bombarded with one slow neutron, it will split into two nucleus, plus in this 3 neutrons are released and followed by some energy. That's it. Means here, when a heavy nucleus is bombarded with a slow neutron, gets split into two almost equal nuclei. This process only we can call it nuclear fission. So let us take example, children, then you will understand, better understanding you have. So let us take here uranium 92-235. When it is bombarded with a neutron, children, what will happen? It will absorb, the uranium will absorb, then it will convert into uranium 92-236. Here I am putting a star point, which is more unstable. Then immediately what will happen? It will undergo decay. It will just split it into two nuclei. So here it is barium 56 144 and here krypton 36 89, and in which 3 neutrons are released followed by 190 mega electron volt. 190 mega electron volts. Very important. In exam they'll ask you a question, how much amount of energy is released in each nuclear fission? 190 mega electron volt is released. Children, it is not compulsory that always uranium should get decayed into barium and krypton. It is also possible that 92-235, yes, absorbed one slow neutron, yes, will become more unstable, and which will convert into lanthanum. It is 57 149 plus it will bromine 35, it will be 85 plus 3 neutrons, and here 190 mega electron volt energy is released. 190 mega electron volt released. But how to calculate this energy? Very simple. So of course now we are going in detail about this. Children, if you want in detail discussion how we got this much energy, yes, already I told you that links will be given in the description. There very clearly it is mentioned how to calculate the mass defect. So in this, actually the mass defect is approximately 0.20 what we can say AMU. So when you substitute this, so E is equal to 0.20 for 1 AMU. How much amount of energy? 931.5 mega electron volt. Then if you can do this, you will get almost 190 mega electron volt energy. Means this much amount of mass disappears here. There will be a mass, this much amount of 0.20 AMU mass defect will be there, which means this much amount of mass is disappearing. So then 190 mega electron energy is released. Clear? Fine, children. And here the one important question is that here, during this nuclear reaction, children, during these nuclear reactions, whatever these 3 neutrons which are released, children, they won't, what we can say, stay calm actually. Then what will happen, you know? Yes, they will initiate again. See, in each nuclear fission, children, 3 neutrons are released. Again, these 3 neutrons will initiate 3 fissions. 1, 2, 3 fissions. Again each fission, again 3 neutrons, 3 neutrons, 3 neutrons. So this process is continued, means the number of neutrons are multiplied. So number of fissions, nuclear fissions are multiplied. So the amount of energy which is released also what multiplied continuously. As a huge amount of energy, what we can say is released continuously, the blast, it may cause to blast. Yes or no? So this type of nuclear fission we can call it the uncontrolled chain reaction, where which are released will initiate continuously nuclear fission reactions, like it goes like a chain, uncontrolled chain. It is called uncontrolled chain system, uncontrolled chain reaction. Based on this only nuclear bomb will work. Okay, very important. So it's a nuclear bomb, children. Nuclear bomb works on what, children? Here, uncontrolled chain reaction, uncontrolled chain reaction. Chain, it's a destruction, what we can say, it's not for a good cause, it's a bad cause, I can say that. But children, as we know, the 3 neutrons are released somehow by using moderators such as heavy water, graphite. If you can control 2 neutrons out of 3, if you can make only 1 neutron to initiate a nuclear fission, other 2 electrons come down, then what will happen? In each fission reaction 190 mega electron volt is released, 190. And in that again, see, in the first fission reaction, for example, first 1 neutron, in each fission reaction 3 neutrons are released. Again these 2 are controlled, they won't participate, they won't initiate nuclear fission. Again will undergo, it will make a 3. Again these 2 are controlled, again this will initiate. Here 3 means in each stage we are controlling the 2 neutrons, so that only 1 neutron is initiating. So that what will happen, so a continuous the control, some amount of energy which we can control is released. Let us say here 190, 190, 190. This energy which is released can be utilized, and this kind of chain reaction is called controlled chain reaction. Based on that only nuclear reactor will work. Nuclear reactor will work based on what, children? It's a controlled chain reaction. Controlled chain reaction. It is good cause, it is for a bad cause, it is good cause. It depends, it is in our hand where we want for good cause or bad cause. So let us use for good cause only. Okay, now fine, children. Now let us think last one, nuclear fusion. Nuclear fusion, yeah, thank God. So some students are feeling, yes, we almost come to an end, we are going to finish our radioactive chapter revision. Yes, children, yes. So that's very, very important actually. Just keep it, continue, have the spirit, have the patience, have the interest. Let us complete each and every chapter before exams nicely, so that you have a great performance with which you are happy, your parents are happy. Children, the very important thing is that here, the best gift, as a kids, as a children, what best gift you can give to your parents? Your results. Just get the best results and see your parents, how proud they feel, children, how great way they'll talk about you. That is the best gift which you can give to your parents. Please try to understand parents' feelings, that's very important. So they are doing so many things for us, children. Then what are we doing? Doing that they will expect some properties, money? No. Our good future they are expecting. Yes, let us give that confidence that yes, dear parents, we are going to have the bright future. Okay, no? Chalo, let us continue that. Okay, fine. Nuclear fusion, children. Fusion means what here? Quite opposite to fission. In a fission, heavy nucleus got splitted, but here two smaller nuclei will get fused and will form a heavy nucleus. And in this process also some amount of energy is released. This process we can call it the nuclear fusion. But children, so this is the main reason for the energy production in the sun and stars. Sun and stars here. Stars, no, sorry. Very bad in English here. Stars, fine. But here, during this nuclear fusion actually, the protons should come together. And we know that protons are positively charged. But how? First of all, positively charged particles, they don't come together. But they have to come together and they should get fused. The very important thing is that that's what these nuclear fusion reactions, they won't occur at ordinary temperatures. They occur at only very high temperature, 10 power 7 Kelvin temperature only. That's what these nuclear fusion reactions are also called as thermonuclear reactions. Thermonuclear reactions. Thermonuclear reactions. Clear? Fine. Let us see the example. Mega electron volt. So in a nuclear fusion reaction here, 4 hydrogens are combined or fused to form a helium, in which 2 positrons, 2 neutrons and 26.7 mega electron energy released. And here an important thing, children, in which either in nuclear fission or fusion, more amount of energy is released per nucleon. But generally blindly, many students will say that, sir, 190 mega electron volt, it is a nuclear fission. No, it's wrong. So look at here. If you can say uranium 235, how many nucleons? 235 nucleons are participating, so that 190 mega electron volt is released. But whereas here, how many? 4 into 1. Only 4 nucleons are participating and 26.7 mega electron volt energy released. Mega electron volt. So it is a nuclear fusion. See, 235 are responsible for 190. Just 4 are responsible for 26.7. So hence, more amount of energy is released in nuclear fusion per nucleon. Achha children, one important point I forgot. I think some students are thinking, sir, you discussed, hope it is clear? Fine. Sir, you discussed about alpha, beta, gamma. But sir, you did not discuss what will happen when alpha, beta, gamma will pass through electric field. Yes, children, I forgot. So as when I was discussing about this, just I got to know that. Let us discuss that. So children, here, if you can just, in general, what will happen, children? This radioactive source is placed in a lead cavity, so which provided with a narrow hole. In exam, they ask this also. Why it is placed in this lead box only? Children, here, if radiation will go all the sides, will get absorbed. It won't be emitted. Means only from this portion only will get radiation. From this portion only will get radiation to get the only narrow beam of radiation. Okay, fine. Now let us say here, let us say electric field is applied. Electric field is applied. Here positive. Here is negative. So very much, don't by heart. Alpha will go left or right or not like that. As alpha particles are positively charged, beta particles are negatively charged, gamma zero charge, which means what here? Alpha particles will get deflected towards negative terminal. Yes, so they'll get deflected like this. They'll get deflected. Okay, alpha. This is alpha, because as they are positive charge, they'll go towards negative. What about gamma? Sorry, beta. Let us see. Ting, ting, ting. So if you can see, beta particles are deviating more than alpha. Beta particles are deviating more than alpha. Why? Because beta particles are very light particles. You imagine they are like a thin. Alpha particles are heavy. So which one will bend more? Heavy one or thin one? Obviously thin. Not in some special cases. In general, I am talking here. So as a beta particles are very light particles, they have very less mass. They will deviate more than alpha. What about gamma? Yes, my dear children, coming to that point. Yeah, I wish I had a scale. Okay, now like this gamma. So the gamma won't listen to anyone. Either it is a electric field or a magnetic field. They don't listen. I don't care. Gamma ray will tell. Gamma radiation will tell. I don't care, bro. With your electric field or magnetic field, you can't show any effect. Why? Because I am a chargeless. I am a massless. Yes, children. As a gamma radiations are chargeless and massless, there is no effect of alpha, or there is no effect of electric field and a magnetic field. Is that clear? Fine. With this successfully completed, what we can say, radioactivity. Children, this is only what? Just one short video so that you can have a quick revision. If you need in detailed discussion of this radioactivity chapter, yes, links are given in the description. Just kindly go through that. Okay, fine, children. So it's very, very important. Just I keep on telling you every time, Yes, especially this chapter, it's a purely conceptual. You must read the textbook. It's my humble request. My humble request. Please read the textbook, children, ultimately. So whenever you are reading the textbook, children, yes, keep our notes with you, so that whatever you feel important part, yes, you can note down. So that notes also very useful to you when you are doing a quick revision. Okay, children, fine. So in next class, what we'll do, yeah. So many students are there sending a mails by asking us to make a one-shot video on household circuit. Yes, children. So even household circuits also, yes, already household circuit videos are uploaded. Just kindly watch, just go to the playlist. There you will find household circuit, but one-shot video is not made, and even sound also one-shot video is not made. And other students also are asking, to make a video on the numericals of current electricity. Yes, children. Yes, we are noting down everything, all your requests. Yes, accepted. We will make, but please excuse us. So due to busy schedules, we are unable to upload continuously. We'll try a little bit. But children, so in the next almost 1 month, let us say by the end of the December, so complete 10th class, all chapters. So if possible, all numericals from all chapters also we'll try to upload, and we will support. Don't forget that we are with you. We are there to guide you. We are there to support you, children. Okay, children. Fine. Thank you so much. All the very best.